much, sir. He's come a long way, though. He did his thesis on laboratory plasma physics, working on accelerators, and thankfully for us, moved on to the bigger and better things, and worked on a diverse variety of topics, ranging from microlensing planets to black hole astrophysics to the big questions about the universe. And the two of those that I think he's most infamous for these days, the 21-centimeter cosmology and where the first stars and galaxies came from. And on that note, he has a new book out, which you can now go buy on Amazon. How did the first stars and galaxies form? And I'm sure he'll sign it for you. I think he's going to tell us a little bit about that today. So thank you.
Thank you, Avery. It's a great pleasure to be here. And what I'd like to do is mention a few highlights. This is a subject that has been around for a while, at least a couple of decades. Back when I started working on it in the early 90s, there were only a few people interested in it. But now it's becoming, and I think over the next decade, it will be a major frontier because of all the observational projects, some of which I'll describe. Now, I just want, before starting, to mention the underlying assumptions that we all make. And we have to keep those in mind because they were not tested observationally well enough. So perhaps one of these will break down, and we will be surprised. So we are assuming the standard model of physics, of course, that the initial conditions came from inflation, scale invariant, close to being scale invariant, and that the dark matter is made of weakly interacting cold particles. And any of these assumptions, if they end up being falsified, they may be providing us with surprises. So that's why it's important always to verify. Just like when you cross the street, you want to verify that the car will not run over you, even though you have the right to cross the street. The same is true here. We want to make sure that these assumptions that we make are indeed valid, especially since we haven't yet identified the dark matter particle. And as Avery mentioned, this is a book that I just finished this year, and I just got the first hard copy last week. And you can see this big question mark here. That's the reason I put it here. We do not have an answer to the question. And that's why it's an interesting frontier to get into. So if there are any students in the audience, that's a very interesting topic for a PhD thesis. And many of the things that I'll describe today are mentioned more pedagogically in the book. I focused mostly on the physical principles because they are probably more likely to survive the scrutiny of the next decade of data, and less so with a definite answer to this question. Now, the initial conditions of the universe can be summarized on a single sheet of paper. And this is the sheet of paper. We have it. And we have error bars on all various cosmological parameters. And in principle, we can fit those into a computer simulation. And as long as we keep the resolution high enough and we use the correct laws of physics, we will end up reproducing the observed structure in the universe today. The amazing thing is that even though you can summarize this initial data on a single sheet of paper, if you wanted to summarize the present-day conditions, you have to use thousands of books in libraries that cannot even capture the complexity we see around us today. So somehow, all of the complexity we see around us, including politics and people, emotions and everything, it's all encoded in these very simple initial conditions. And gravity made everything else, right? That's an interesting point to realize. This is sort of like a summary of the present-day universe. And in terms of observing, we have obviously observed the cosmic microwave background 0.4 million years after the Big Bang. We have observed galaxies about 1 billion years after the Big Bang, but we are missing some pages in this photo album of the universe that we haven't yet observed. And this is a more quantitative way of presenting it. If we are sitting here today, there is a certain volume around us that we can observe, and that's the volume associated with the speed of light times the age of the universe. That's how far we can see. The Big Bang is 13.7 billion light years from us. And this is as much as cosmologists can probe in principle. You can ask which fraction of this co-moving volume was observed so far. So this beautiful data set that I mentioned to you, all the error bars on the cosmological parameters, turns out that they were derived, for example, from the Sloan Digital Sky Survey near us, out to a redshift of around 0.3, and from the cosmic microwave background data that is associated with a two-dimensional shell around us. And if you ask how much volume is associated with these data sets, it turns out to be 0.1% of the observable co-moving volume. So only 10 to the minus 3 of the volume was observed. That's why we would like to actually map the distribution of matter in the remaining 99.9%. And that's why the young people have a lot to do in this context in the future. And so obviously, we will learn much more about the initial conditions. The error bars will get much narrower. But also, we might uncover new physics. And so that's why it's very tempting to image 99.9% of the co-moving volume of the universe. Now, how can we do that? You can see here the different redshift shells, redshift 1, redshift 2, and that's in co-moving coordinates. And we believe that the universe was ionized at around redshift of 10, which is roughly, as you can see, half the volume. And so if we have a way of mapping the distribution of matter around that epoch, it will go a long way towards imaging a substantial fraction of the observable universe. In terms of the standard picture of cold dark matter, you can do a simple calculation of the abundance of halos, dark matter halos, the number per unit co-moving volume, per unit mass, divided by the mean density of the universe, and times the mass of the halo squared. So that tells you how much mass there is in halos per logarithmic bin of halo mass. And of course, at very high redshifts, above 50 or so, a very small fraction, exponentially small fraction of the mass was collapsed into halos. But once you get to a redshift of 20 or so, you see here you start to already saturate the same level, the same collapsed fraction of mass as you find today. The only change that happened between redshift 20 and the present time is that at this level of amount of mass per logarithmic halo mass interval, basically today we have many more decades, many more bins in this log halo mass space. So today, the nonlinear mass scale is around 10 to the 14 solar masses or so, groups of galaxies. And back at redshift 20, it was associated with 10 to the 5 solar masses or so. But other than that, there was the same amount of, roughly the same amount of mass collapsed into halos per logarithmic mass interval, already at redshift 20. And all that happened is this gradual progression towards the curve at redshift 0. And the first galaxies formed just like present-day galaxies. They formed at the intersection of sheets and filaments. And the process that was responsible for their formation had to do with cooling of the gas, primarily by molecular hydrogen. But there are two ways in general that you can think of in terms of mapping the distribution of matter. You can use galaxies as sort of test particles that follow the dark matter and therefore trace the filaments and sheets in the distribution of matter. Or you can survey the diffuse gas, the intergalactic gas. And I'll try to describe both of these methods. So let's start with the galaxies, or the stars. One topic that is part of the title of this talk has to do with the reionization of the universe. And we can ask, what are the requirements? How many photons do you need to produce in order to ionize the universe? Obviously, you need to produce at least one ionizing photon per baryon. You may need a few more because there are some recombinations in overdense regions. So just to produce one ionizing photon per baryon, this is the mass density per unit volume in the universe, per co-moving megaparsec cubed, that the mass in stars per megaparsec cube that needs to be produced in order to have at least one ionizing photon per baryon for a Salpeter mass function of stars, for a mass function similar to what we find in the Milky Way. So you need roughly 10 to the 6 solar masses per cubic megaparsec if all the photons are able to escape And if only a fraction of those photons are able to escape from the galaxy, then you need to multiply by the escape fraction to the -1. Now, once you ionized hydrogen, you also need to compensate for recombinations subsequently. It's not sufficient to just ionize the universe, because the recombination time, even at the mean density, is equal to the Hubble time at a redshift of 8. So in order to keep the medium ionized, given the overdensities, you need to produce new photons to keep it ionized. And that's a different calculation. And many observers make the mistake of switching between these two. So if you hear an observational talk, often people will say, we'll use this expression as a prerequisite for ionizing the universe. That's not true. First, you need to produce 1 photon per baryon, and then you need to compensate for recombinations. And the number to compensate for recombinations has also units of rate per unit time. You need to produce stars at a rate of 10 to the -3 solar masses per cubic megaparsecs per year. And that depends on the clumpiness of the gas, also depends on the escape fraction inverse, and on the redshift, 1 plus z cubed, because the recombination rate scales like the density squared. So these are 2 requirements, and we can ask, if we look at the galaxies that we see, do they satisfy at redshift 6 or above? Do they satisfy these requirements? And here is one diagram like that. It shows the stellar mass density, the cumulative mass in stars per unit volume in the universe as a function of redshift. Okay, so redshift 0 is here. We are approaching 10 to the 9 solar masses per cubic megaparsec today. And as we go back in time, less than 1% of those stars was produced at redshift 5, when the universe was roughly 1 billion years old. It's an interesting number to keep in mind. So the first stars that were responsible for reionization were less than 1% of the present-day population of stars. However, if we just count the number of galaxies that we see and their UV luminosity, we just don't get sufficient ionizing photons per baryon. So this red line is what you would get if the escape fraction was unity from those galaxies. And it's clear that we are missing some of the star formation at redshifts above 5. And there is a similar plot that was extended very recently with Hubble Space Telescope observations, all the way up to redshift 8, as you can see here. The measurement is basically you are counting how many galaxies. So first of all, you select galaxies photometrically. And I'll show that next. So let me describe So the current data was obtained from a new instrument on the Hubble Space Telescope with the Wide Field Camera 3 in the infrared. And just to give you the state of the art right now, 100 galaxies are known between redshift 7 and 8. 100 galaxies as of last year. All we know is the luminosity. We don't know the halo mass. But we are talking about roughly 10 to the 10, 10 to the 11 solar masses in that range, if you are, in terms of halo masses, in terms of the abundances. But let me describe first how these galaxies are selected. So these galaxies are observed, obviously, photometrically. We don't have spectra for them. And it's using basically the dropout technique. If you observe it at some filter, for example, the H band, but you don't observe the galaxy or the source in the J band, then this is the probability distribution of redshifts that you should assign to this source. And here the drop is just due to Lyman alpha absorption by the intergalactic medium and the interstellar medium within the galaxy. So interpreting the drop in the flux as associated with Lyman alpha frequency, you can figure out the redshift. And J dropouts are redshift 10 candidates. Okay? And then if you have other bands where you see the drop, there are low redshifts. And here is another example where you see a Y dropout. So you see the galaxies in H and J, but not in the Y band. And that's more likely to be around redshift 8 to 9. And so that's basically you are counting how many galaxies you have per co-moving volume, because you know the redshift roughly. And then from the UV luminosity of those galaxies, you have to convert that into a star formation rate. Okay? And there are various conversion standards. And there are some issues there, for example, with the initial mass function of stars, because the spectrum of a galaxy depends on that, with the assumed star formation history of the galaxies that you're observing and so forth. So there are some uncertainty. But those uncertainties affect the error bars, the large error bars that you see. And the most important issue is that the observers can see only the brightest galaxies, and you are missing most of the star formation at those redshifts. That's something the observers do not fully appreciate. And here is, for example, the number of galaxies per magnitude per cubic megaparsec as a function of magnitude. And people are going all the way up to redshift 10 right now. So this is the red line with respect to keeping the medium ionized relative to recombinations. And you can see that the present-day data goes even below that. So clearly, we're not seeing most of the star formation. This is a theoretical prediction that in a paper that we wrote in 2000, 10 years ago, where we tried to calculate from basic principles what we should expect for the star formation history of the universe. And for reionization at redshift 10, that's the middle curve here, we expected 2 orders of magnitude more star formation than they are observing. And the reason is very simple, that most of the star formation takes place in galaxies that are way below the detection sensitivity of the Hubble Space Telescope right now. And even with the James Webb Space Telescope, it would not be possible to see most of the star formation. So we are talking about, in terms of HST, we are talking about a detection sensitivity of order 10 nanojansky in the infrared. JWST will push it down to 3 nanojansky at 10 sigma. And then most of the star formation is below a nanojansky per source.
It's not show up at the infrared background.
Well, if you can't resolve the individual sources, then it will be a contribution to the infrared background. Then you should analyze fluctuations in that. The problem with the infrared background, if you don't identify sources, is that you have contamination from the zodiacal light, for example, and foreground sources, and you need to filter those out. So the future is with the James Webb Space Telescope, and it's scheduled for launch in 4 years. But as I said, even the James Webb Space Telescope will not be able to resolve most of the star formation. There are also plans to build very big telescopes, and I attended a conference just a couple of weeks ago on how these telescopes will complement JWST. People are thinking about that. All of these teams claim that they have some funding already on the way at the level of 400 million or so. They're still missing about 2/3 of the construction cost, not to speak about the operation cost. But all of them prefer to go in their path without collaborating. So in other words, there are 3 different telescope designs, and right now they are not willing to compromise and collaborate with any other team. And one of them is the Giant Magellan telescope that has 7 mirrors, each of which is 8.4 meters in diameter. And then there is the 30-meter telescope, a segmented aperture of 30-meter diameter. And then there is the European Extremely Large Telescope, 42 meters in diameter. And one has to keep in mind that these telescopes offer a very important advantage relative to James Webb, the James Webb Space Telescope, in that they can resolve individual galaxies. So even if you keep the halo of a galaxy to have a fixed mass and you just change the redshift of the galaxy, since the universe has a density that goes up as you move back in time, like 1 plus z cubed, the size of the galaxy would also shrink roughly like 1 over 1 plus z. So for a fixed halo mass, galaxies should become more and more compact as you go to early times. And in fact, this was observed at redshifts 2 to 4. So JWST will not be able to resolve galaxies at redshift 10 simply because of the fact that the universe was much denser back then, but also because the galaxies were smaller in mass. And in order to resolve them, you really need a ground-based telescope, something of this magnitude. So that will be very important in terms of identifying the nature of these unresolved sources that JWST sees. In terms of theoretical work, and I'm sorry that the projector is cutting off the bottom, we made significant advances in terms of simulating the sites of star formation early on. So this is an example from a computer simulation by Naoki Yoshida, Volker Braun, and collaborators, where you can see that you start with a cosmological halo of these very early galaxies that have 10 to the 6 to 10 to the 8 solar masses. And then you can zoom in down to the scale of 10 astronomical units, and basically the scale of the solar system, and see how possibly, if you go even farther down to the scale of a star, how gas accumulates on the surface of a star. Of course, in these simulations, there was no nuclear fusion ignited at the center of the star, and there is an important issue of feedback. What happens once you ignite the star? How that affects the infall of gas to feed the core, the inner region, and what would be the mass limit on the star as a result. People are finding something that they haven't found before, and that's the formation of binaries in the first generation of stars. These are called population-free stars, metal-free stars. And there are 2 independent papers reporting binarity as a natural consequence of these sites. In terms of the mass of these early stars, these are plots from present-day stars and in different environments. And you find that in all these different environments of star formation, there is a characteristic mass, okay? And it's around a fraction of a solar mass. And the idea is that in the early universe, because the temperature of the gas was higher, actually there was a temperature floor of the CMB. The microwave background had 30 degrees Kelvin at a redshift of 10. So presumably the gas was hotter. Also, it was not easy to cool it below a few hundred degrees Kelvin. As a result, the mass accretion rate onto the stellar cores was much higher than in the present-day interstellar medium. That's because on dimensionless grounds, the mass accretion rate is the sound speed cubed over Newton's constant. So if you increase the temperature of the gas that feeds the core, then you increase the mass accretion rate. And then during the first million years, the star is able to grow much more rapidly than present-day stars. And so that led to the idea that the first population of stars had a much higher mass than the present-day stars, more like tens of solar masses or maybe hundreds of solar masses than a fraction of a solar mass. So an increase by 2 orders of magnitude or so. Now, of course, massive stars can either end up making a black hole, or they can end up in a supernova, a peri-instability supernova. And in fact, Dick, early on in his career, worked on things related. Right, Dick? So actually, as of 2007, and this is a paper written just last year, I mean, it was posted on AstroPH in January. There is a supernova, 2007 Bi, which is an excellent candidate for a peri-instability supernova, the kind of supernova you might get from population-free stars, metal-free stars, in the mass range between 140 and 260 solar masses. And the reason people associate these supernovae with low metallicity stars is because massive stars usually lose their mass by winds if they have a high metallicity. So in this particular explosion, the nickel mass was around 5 solar masses, very large. And the ejecta mass was of order 100 solar masses. And given what we see in terms of massive stars losing their mass by winds, the only way to achieve that would be to have a star with very low metallicity so that wind mass loss is not so significant. The amount of energy released here was 10 to the 53 ergs. So you can see here the light curve compared to 87A. It's much higher and much longer duration. And basically tells you that this is a very unusual type of supernova. So we have one example already from a local dwarf galaxy, a nearby dwarf galaxy, at a redshift of 0.13. And having metal-free stars that are quite massive makes reionization actually easier. The reason for that is that these massive stars had an effective temperature which was more or less fixed at around 10 to the 5 degrees Kelvin. They are held by radiation pressure, so the luminosity is equal to the Eddington limit, which is proportional to their mass. And if you consider masses above 300 solar masses, you get, during the lifetime of these stars, which is always a few million years, you end up producing 100,000 ionizing photons per baryon that was incorporated into those stars. And this number is much higher than the number of ionizing photons that you get per baryon for a salpeter mass function. There you can get, if the metallicity is not 0, you get a few thousand ionizing photons per proton incorporated in the star. And this is an important number. This number tells you, as a result of the fact that baryons were assembled to make such a star, how many more baryons was this star able to ionize? And here the gain is a factor of 10 to the 5, while for a salpeter IMF, it's only a few thousand. And this is an example for how much flux you observe on Earth per million solar masses as a function of wavelength for a star cluster at a redshift of 10. And of course, the very strong UV emission from these hot stars, 100,000 degrees Kelvin, is getting reprocessed by the surrounding medium. So you can get helium recombination lines, such as the 1640 angstrom line, in addition to Lyman alpha. So there could be very strong lines associated with helium because these stars are very hot. And of course, one can drive, I mean, these strong UV emitters can drive winds. And a very important process to consider in this context is the Lyman alpha radiation pressure, which, as it turns out, around mini-halos. So if you consider a single star of 100 solar masses embedded in a halo of 1,000,000 solar masses, turns out that the radiation pressure force is bigger than gravity due to the Lyman alpha line by a factor of 100. So you can easily push the gas out as soon as a single star forms in such a halo. And it's very likely that these halos had only one star in them, so they were not really galaxies. They were a star embedded in a dark matter halo. And then a similar process could take place in starburst galaxies. You could also show that there are super winds that could result from Lyman alpha radiation pressure. And I don't have time to get into the details. Now, there must have been a transition between population 3 stars that were high mass, low metallicity, and population 1 and 2 stars, the type of stars that we see nowadays, as a function of the metallicity. Once the metallicity was above some threshold, the mass function converted into the present-day mass function. And if you just consider carbon and oxygen, singly ionized carbon, neutral oxygen, can cool by atomic transitions, you find that at a metallicity of 10 to the minus 3 solar, already these atomic species cool the gas more effectively than molecular hydrogen. So the transition to low mass stars occurred as soon as the gas was enriched by 10 to the minus 3 solar. And if you include dust and molecules, like CO, for example, the transition could have taken place at even lower metallicities. So very little enrichment is sufficient to make the transition. And of course, one prediction in this context is that if we now observe stars in the Milky Way halo, and we can only observe low mass stars because they are long-lived, the high mass stars are gone by now. We cannot see them. So if we observe a low mass star with an extremely low metallicity below these thresholds, then that's in conflict with this whole idea. But so far, even though people found anemic stars, stars that lack iron, that are anemic, the carbon or oxygen level was above 10 to the minus 3 solar. And the one thing to keep in mind is that the first galaxies were very strongly clustered on large scales, actually, not small scales. And that's simply due to the idea of bias that Nick Kaiser, that used to be here, pioneered in the 80s. Basically, you can think of the galaxies as the highest density peaks in the underlying matter distribution. And at a redshift of 20, the fluctuations did not grow much. So you are picking up the highest peaks. And actually, this structure that is shown here is on scales that go up to 100 co-moving megaparsecs. That's the thing that the community that works on this subject failed to appreciate for a while, even though we tried to argue this for at least 5 years before the simulation people realized it. The point is that you need a simulation box of at least 100 megaparsec in order to get a fair sample of how the very first structures form in the universe, just due to the idea of bias. And you can see here an example where the galaxies form these large structures on scales of 100 megaparsecs. These are the black points compared to the other points, which are the matter distribution. So as you go to lower redshifts, of course, the bias becomes less severe. But the thing to keep in mind is that the very first regions to be enriched were these high-density regions. And, of course, in order to get a first sample of the universe, you need a simulation box that is as large as 100 megaparsecs or bigger, that resolves dwarf galaxies, very small galaxies forming early on. And that was a big challenge for numerical people because of the dynamic range that it requires. And you need to follow gravity, hydrodynamics, radiative transfer. And that was achieved only over the past few years. It was not true a decade ago. In fact, the very first simulation boxes, for example, that Nick Nedin used, were 1 megaparsec in size. Of course, if you take one atom, you will find that reionization was instantaneous, right? So you really need 100 megaparsecs or more to get the universe, to get a first sample of the universe. And then, of course, the enrichment also was inhomogeneous. So in the high-density regions, the universe was enriched early. In the low-density regions, it was enriched late. And so you can have population 3 stars in high-density environments early on, but later you might find those population 3 stars in low-density environments. The universe did not follow the same history. We might even find pockets nowadays that make population 3 stars. So let me show you an example for a simulation. Oops. One of the simulations that we worked on with Heat Track and Renew Sen that illustrates how reionization may have progressed with and without population 3 stars. So on the right, you see a mix of population 2 and population 3 stars. And on the left, population 2 stars only. And you can see that these regions that get ionized, these are the red regions, grow much faster if you allow for population 3 stars. And clearly, population 3 stars are producing many more ionizing photons per baryon. They are much more efficient at getting reionization completed early. And you see the inhomogeneous nature of reionization, with the low-density regions being ionized last. And the redshift was shown here. Now it's redshift 6 or so. We started at a redshift close to 20. So the fact that reionization was inhomogeneous has, of course, implications. First thing is the Jeans mass, the minimum mass of galaxies in the intergalactic medium was increased because the medium was heated by reionization. And the minimum viral temperature of galaxies was raised up to about 10 to the 5 degrees Kelvin as a result of reionization. That's something that people have to keep in mind when modeling the distribution of galaxies. And then, of course, the clustering of galaxies was also affected as a result of this inhomogeneous heating. And these effects need to be kept in mind. Now let me mention very briefly black holes. I mentioned stars, but there is an interesting point that we expect the universe to have been ionized, reionized at around the redshift of 10, and we believe that it was done, the reionization process was done by stars, not by quasars. And an interesting question is why? Why weren't black holes responsible for ionizing the universe? And on that point, I just wanted to mention an interesting coincidence that if you consider redshift 10, and you ask what is the time it takes for a galaxy to double its mass, and that's the time it takes to make new stars, to double the amount of mass in stars, turns out that this time scale gets shorter than the Eddington time for the growth of black holes, at around a redshift of 10. And so it took black holes more time to grow than for stars to be formed at those very early times. And that's possibly the reason why the universe was ionized by stars and not quasars. And speaking about black holes, if you write the luminosity from a quasar as some radiative efficiency times the mass accretion rate, there is a characteristic time for the growth of a black hole, and that's the mass of the black hole divided by this mass accretion rate. That's the Eddington time, which is 4 times 10 to the 7 years for a radiative efficiency of 10% at the Eddington limit. And of course, the solution to this equation is exponential growth on the Eddington timescale. So if you ask, we observe quasars at a redshift of 6 that have around 10 to the 9 solar masses. Can we grow these quasars out of stellar mass seeds in 1 billion years, which is the age of the universe at that point? Turns out that you barely can make it. If you keep feeding the black hole steadily, then you can start with 100 solar mass seed from a population 3 stars and grow all the way up to 10 to the 9 solar masses in just 1 billion years. But you barely make it. And that's why I think it's not very likely to be the case. And I'll mention a reason for that. That's gravitational wave recoil. Galaxies form hierarchically in the universe. So if 2 galaxies have a black hole at their center and the 2 galaxies merge, the 2 black holes will come together and eventually spiral in by the gravitational wave emission. And then if one of the black holes, let's say, is smaller than the other one, then at the end of the process, it will plunge towards the bigger black hole and emit a burst of gravitational waves in a preferred direction. Because of momentum conservation, the anisotropic emission of gravitational waves will result in a recoil of the black hole remnant. And so this recoil speed was calculated over the past couple of years by numerical simulations. Turns out to be typically at the level of hundreds of kilometers per second. But it can go all the way up to 4,000 kilometers per second. At any event, this kick velocity is much larger than the escape speed from the first dwarf galaxies that existed, which had an escape speed of a few kilometers per second. So what that means is that, for example, if you had a star orbiting the black hole, the star, in principle, would be bound as long as it was orbiting the black hole closer than, or its orbital velocity was higher than the kick velocity. But just the mere fact that the black hole gets kicked implies that you just cannot keep the black hole at the center of the potential well. You can't sustain this steady feeding of the black hole with gas throughout 1 billion years without the black hole moving out of the system for a while and not being fed for a while. So that's why I think it's not likely that these black holes were fed continuously. And in fact, this process of kicking black holes from dwarf galaxies, this can be tested observationally. If you look at the Milky Way halo, the Milky Way halo was made out of building blocks, each of which were a dwarf galaxy. And if this process took place and the black holes were kicked out of the centers of these dwarfs, they would take with them some stars in the process, those stars that were orbiting close to the black holes. And in principle, we can search for floating star clusters, compact star clusters in the Milky Way halo. And this is an idea we proposed with my student, Ryan O'Leary, and we are looking now through the SDSS data set, because these star clusters should have been observable in the SDSS data set. But, yeah.
Clusters being the black hole is kicked out of the center of the galaxy,
Right.
remains bound to the galaxy.
No, so if you imagine the region that ended up making the Milky Way galaxy, in linear theory, linear perturbation theory, the depth of the potential well for an omega equal 1 universe doesn't really change. So the potential well of the Milky Way galaxy was already produced at inflation. I mean, And when the galaxy collapses, you only gain a factor of 2 or so. So the depth of the potential well of the Milky Way was already in existence in the same region that ended up making the Milky Way. Within that region, there were dwarf galaxies forming early. And they lost their black holes due to these kicks. If the black holes were kicked by 100 kilometers per second, they could not escape from the Milky Way potential. So the black hole star clusters remained bound to the region that ended up making the Milky Way. The escape speed from that is more like 500 to 1,000 kilometers per second, depending on the location. And kicks have a very low probability of reaching those high values. So that's the idea. So if you look today in the halo of the Milky Way, there should be all the debris that was kicked out of galaxies. And that includes, let's say, a black hole, but also all the stars, even if it's tens or hundreds of stars that are long-lived, you should be able to observe a 20th magnitude object in the Sloan survey. And the issue is just to separate all the dwarf galaxies at redshift 0 from those star clusters. These star clusters are very different from globular clusters because they have a dark central object. So they have, for example, the spectral lines, if you take a spectrum, they will be broad. They will have 100 kilometers per second width. In a globular cluster, it's more like 10 kilometers or a few kilometers per second. And so you would see that there is a lot of dark mass, and you can distinguish. But then the question is how to find these needles in the haystack. But it's something that nobody, I mean, Zwicky, when I gave this talk, a related talk at Caltech a year and a half ago, it turns out, I mean, so afterwards, Walt Sargent came to me and some people talked about the fact that Zwicky was, in his catalog, he was looking at redshift 0 clusters or peculiar objects. But since then, people haven't really searched for that, such things. So they may exist, actually. So coming back to the black hole issue, how do you grow a black hole if it's difficult to sustain steady feeding over 1 billion years? And one possibility is that you get a jump start, that instead of starting with 100 solar mass seed, you start with 1 million solar mass seed. And that's possible under some circumstances, as we showed some time ago with Volker Brom. Now this idea became actually very popular recently. There are a number of papers that were trimmed from the bottom of my slide. Another type of black holes that we can hope to observe at these early times are gamma ray bursts. And gamma ray bursts are a result of the collapse of the core of a massive star that produces jets, and you can see them all the way to redshift 10 or 20. And of course, the key observational question is how to identify high redshift gamma ray bursts early enough so that then you do follow-up to look for their afterglows. And the key threat, sorry?
You said this as if this was a proven time.
That they exist.
No. That if we go back, right?
Yeah.
I mean, there's little, I completely agree with you that that's probably what they are, but it is a bit of a strong statement to say that's definitely what they are.
The gamma ray burst, you mean the long duration. Well, the key evidence for that is the existence of supernova in the afterglow light curves after a while. The fact that you can associate them with type 1c supernovae. You can associate them with type 1c supernovae that lost their envelope. You see evidence for the light curve of a supernova.
That doesn't necessarily mean universal one-to-one.
No, there could be other, but since the first stars were massive, an interesting question is, could they result in gamma ray bursts?
Well, so an interesting question for me is whether being among the
That's right, that's right.
it's slightly different realms.
Yeah, so that's exactly the point. So theoretically, that's exactly where I am here. And the question is, could a population 3 star be a progenitor of a gamma ray burst? This question doesn't have a good answer at the moment. And I would encourage people to do more research on that. I don't have the answer. There are some requirements to get a gamma ray burst. You need sufficient angular momentum so that you can power a jet from the central black hole. And there are also issues related to binarity and winds, mass loss, and so forth. I don't want to get into that. But the highest redshift gamma ray burst that we observed so far is 8.3. And the observers are not very efficient at catching those. So there might have been many more that were missed by people that use the Swift dataset. Even this one was looked at too late to get a very good photometric detection. And in fact, they tell me that they have a candidate even for redshift 12, but it's not clear. Because they are not efficient at catching it very early. That's the problem. And so that's an interesting frontier for observers, to try and have an alert system that uses an infrared telescope and follow up on candidates early enough. And with JWST, it should be possible, if they exist, if these gamma ray bursts exist, it's a piece of cake to see them all the way, the afterglow, all the way up to redshift 15 or 20, whenever they exist, because the sensitivity of JWST is way below what you see in the afterglow. The key of using afterglows instead of quasars, so traditionally, if there are old observers in the audience, they would tell you that people used quasars to probe the intergalactic medium. But by now, we have a redshift record held by a gamma ray burst, not by a quasar. And in principle, we would like to use them as beacons of light to probe the intergalactic medium. The problem is that they usually have damped Lyman alpha absorption associated with the host galaxy. And at least in all the cases that we looked at, it was not possible to say anything about the intergalactic medium because of that. Another interesting point that I wanted to mention is that polarization is expected in radiation that is being scattered from a galaxy by the intergalactic medium. And so far, the observers did not really pursue this frontier. In fact, you would expect polarization at the level of 30% in the Lyman alpha halo around galaxies. So now let me move to the diffuse gas. I described stars and interesting tidbits about them. Now let me move to the diffuse gas. And of course here, this is a cartoon from a Scientific American article that I wrote. The idea is that the first stars and then the first galaxies produced ionized bubbles around them. And the bubbles are delineated here in red. And they grew in time, and eventually the entire medium made this phase transition to fully ionized. And one way to probe neutral hydrogen is through the 21 centimeter line. And you are all familiar with it. It's basically a transition between two states of the ground state of hydrogen, in which the spin is either parallel or anti-parallel. The spin of the electron is parallel or anti-parallel to the spin of the proton. And that's the 21 centimeter transition. And you can express the population of the two levels in terms of a Boltzmann factor with some temperature, which is called the spin temperature. And the transition energy is a fraction of a degree Kelvin. So it's 0.07 degree Kelvin. That's how much energy there is in a photon with a wavelength of 21 centimeter. And of course, there are many processes that can contribute to population of these, of the higher level relative to the lower level. For example, collisions, atomic collisions. They couple the spin temperature to the kinetic temperature of the gas. And then radiative coupling to the microwave background couples the spin temperature to the microwave background temperature. And because we're observing the wavelength of 21 centimeter times the redshift due to the expansion of the universe, we have this third dimension. So we can actually image the hydrogen in 3 dimensions and do tomography. It's just like slicing Swiss cheese. At least during reionization, you have these holes of ionized gas, and you are slicing the cheese or the hydrogen at intervals comparable to the size of these holes. Now, an interesting question for someone like Dick is, can you separate the physics from the astrophysics? So I have to define first what I mean by physics and astrophysics, and I hope that I will not insult any of the star formation people in the audience. So by physics, I mean initial conditions from inflation, the nature of the dark matter, and dark energy. Okay, so these are physical parameters of the universe. By astrophysics, I mean anything to do with star formation. Now, of course, star formation is, in a way, an outcome of the initial conditions from inflation. But the problem is we can't use stars to tell us about the initial conditions of inflation, from inflation, because of the large dynamic range of scales down to the point where you make a star. All the initial conditions are being erased, eliminated. You can't really learn about these issues by observing stars form. Okay? And so that's what I mean by astrophysics, anything to do with star formation. And the answer to this question is, in principle, yes, you can use the 21 centimeter line and separate aspects of the physics from the astrophysics. Of course, before the first galaxies formed at redshift above 25, there were no stars. So by definition, we're doing physics. Okay? That's just logic. There is nothing in it other than that. During reionization, you can also separate the physics from the astrophysics by looking at the effects of peculiar velocities, which are induced by gravity. And it's possible to look for those effects by the anisotropy of the 21 centimeter power spectrum. And then after the universe was ionized, there were still dense pockets of hydrogen left over. These were in the damped Lyman alpha systems, in individual galaxies. And it's just like doing a galaxy survey. If you map the 21 centimeter after reionization, you are just doing a galaxy survey without resolving individual galaxies, because the distribution of hydrogen was modulated on large scales, tracing the distribution of matter. So again, you can do what galaxy surveys do, and that's constrain the power spectrum of perturbations. And of course, you can test the gravity by measuring the growth of perturbations on small scales that were not probed so far, which are still at the linear regime in those very high redshifts that we are talking about. I will not get into those details. Let me avoid them. They have to do with how the 21 centimeter signal evolves. There is a Physical Review D paper that we wrote with Jonathan Pritchard, where we laid out the entire history of 21 centimeter. And there are a number of experiments, and this is for Whaley Penn, that is not here. He's in Korea. But he's involved, of course, as you know, in GMRT. But there are others, the MWA, the Murchison Whitefield Array in Australia, that we are partners in. LOFAR in Europe. There is an effort in China. I'm not sure exactly where they stand right now. Paper from UC Berkeley. And, of course, ultimately, the Square Kilometer Array. And each of these observatories has different parameters in terms of course, the site, the frequency range, the area, and the coverage of the sky. And the status, if I had to make an analogy, I would say the status is similar to CMB research, the research of the microwave background anisotropies, prior to COBE. So prior to COBE, you have to understand the psychology of the field was to put upper limits. Just saying, you know, we can rule out the amplitude being above some threshold. So people were putting upper limits until COBE detected the signal. As soon as COBE detected the signal, or a little bit before that, and Dick can tell us the exact history, then the psychology switched, and everyone was detecting a signal. So we are still... Okay. Okay. Well, there...
And it was just by chance that the ones that were on the degree scale didn't get it earlier. In fact, the sub-pole thing that Loeb and company actually did get it earlier than the announcement.
Well, but the reason I bring it up is because often observers dismiss the importance of theory. They say, you know, we don't need the theories. We can just observe the sky and find the answer. And the reason that theory is expected is because observers often miss to discover things because they were not aiming at looking for these things. So, for example, gravitational lensing. Exactly. Exactly. That's my point.
The universe didn't have to cooperate.
That's right.
Here, once again, the issue of how one's using tomography, et cetera, is something, and which region to look at is, I think, as much as anything, theory driven.
Right. I mean, gravitational lensing is another example, and Neil knows that already, where arcs, giant arcs, were in the literature, actually, until people identified them and looked back at some UpJ issues from previous years to see them there. Yeah. So theory is important. In a place like that, I'm sure you appreciate that. So here is an image of, for example, the tiles that are used by MWA. And this is an artist illustration of how they would look like once you construct the entire MWA. There would be 500 antenna tiles. So far, there are 32. And each of them has 16 dipoles, 4 by 4. And they cover an area of 1 kilometer squared or so. They will have a collecting area of 8,000 square meters. Now, this project, the 32 is taking data, so I saw an image of a radio source. Not very impressive, you know. But the amazing thing for me, and that's also an important lesson, is at 2 orders of magnitude lower budget. So these experiments that I mentioned before, LOFAR and MWA, they cost tens of millions of dollars. At a cost of 100K or 200K, there is this experiment. It's basically made of just, you know, wires put together. And this is a single dipole. And the goal of this experiment, that is called EDGES, the experiment to detect the global signature, is to integrate over the sky. Instead of doing 3-dimensional tomography, as I mentioned before, you are just taking the spectrum of the sky. You're integrating across the sky and just looking at the frequency dependence. And if the universe got ionized at some redshift, then you would see a break in the 21-centimeter sky. There was hydrogen before that time, and therefore you had emission at lower frequencies and no emission at higher frequencies. So you would see a spectral break. And you can, from that, constrain reionization by integrating across the sky. So here you see the response of a dipole at 100 megahertz. And this is the sky at 100 megahertz. And you are integrating over the sky, trying to avoid the galactic region as much as you can. So this experiment started already. And it's producing some results. But in a theoretical paper that we posted last week, and that's amazing to me even further. So you have a large community of people doing 21-centimeter cosmology. Then for 1% of the budget, you could have done this experiment EDGES, and only 3 people are working, or 2 people are working on it. Then you would expect some theorists to do theoretical work predicting, forecasting what the observers might find if they do this low-cost experiment as a pathfinder first. There is no theoretical paper on this. So we wrote this theoretical paper last week. And here you see the global signal. This is the brightness temperature as a function of frequency. So that's the black line here. And that's what happens. These are different lines that show you what happens if you shut off, for example, the ionization of the universe. If the universe was never ionized, then you get the dashed line. If the universe was never heated by stars, the intergalactic medium was never heated, so the spin temperature was just declining all the time, then you would get a very deep minimum here with minus 200 millikelvin at 100 megahertz. So for the feedback of the stars on the intergalactic medium, of course, there are various fudge factors. One of them is how much X-ray heating of the gas there was with these early stars, how much Lyman alpha coupling was produced. And you can get different shapes for these globals. This is just the spectrum of the sky. Okay, so it's just like the Kobe experiment taking the spectrum of the microwave background. Here we're taking the spectrum at very low frequencies of the sky, integrating across the sky. And you get different histories depending on what the first stars did. And of course, one is swamped by the synchrotron foreground. So this is basically the synchrotron foreground. It has a power law frequency dependence. But then one can fit it out with polynomials. So if you use a first-order polynomial, you don't fit much of it. Second-order polynomial, that's in black. You fit more. Then you fit it to third order, you get rid of most of it. Okay? So you use a third-order polynomial to fit this synchrotron foreground. And suppose reionization was not a sharp step, but it had some width. Then you can use a simple algorithm to estimate what kind of widths would you be sensitive to here? And practically WMAP has no constraint on the width. This is the width, and that's the redshift of reionization. So WMAP constrains the redshift of reionization. This is 1 sigma, and the red is 2 sigma. With these kinds of experiments, you can put, for example, if you fit the foreground with a third-order polynomial, you can constrain redshift widths of order 2 or less for reionization. And then you can put, using a Fisher matrix approach, you can constrain the redshift of reionization and the width of that. One can, of course, analyze it in more detail. There is a structure to this global signal. So one can pick up the first minimum, the second maximum, the third minimum, and the fourth maximum. So you can constrain those parameters. And I will conclude just with a footnote about what we know about when the universe was ionized based on existing data sets. So, of course, WMAP1 was corrected by WMAP3. And then 5 was more or less in agreement. So that's the optical depth for Thomson scattering. And Planck is supposed to give us very tight limits on the optical depth. But this is a cumulative constraint on an integral along the line of sight. And so if you use also the Lyman alpha forest that redshifts below 6, this is what you get. That's the probability of having the universe with a mean ionization fraction xi at different redshifts. So at redshift 8, most of the medium was probably ionized. You can see that the current probability distribution is peaking around 1. But then as you approach redshift 10, about half of the medium was probably ionized. Redshift 11, it's a smaller fraction. So the universe was probably ionized around redshift 10 based on existing data sets. And that by itself tells you what the 21 centimeter signal should be like. And it's way above the sensitivity of MWA or LOFAR. So just based on existing data sets, we know that we should detect something with these 21 centimeter experiments. And once we do, these probability distributions will get very much narrower, and that's what you see with the black lines here. So once we have the 21 centimeter, we will be able to constrain the redshift history of reionization much better. So in summary, the next decade is promising to be very exciting. There will be large aperture infrared telescopes and radio arrays that will image galaxies and the diffuse intergalactic medium during reionization. And of course, you can work, these different observatories will work in concert. In regions where you find a lot of galaxies, you will not find much hydrogen, and vice versa. And then, of course, on the theoretical side, adequate simulations that are bigger than 100 megaparsecs were only done recently because you need a large dynamic range to capture these large volumes and at the same time resolve very small galaxies within those volumes. Thank you.
We ran a little bit late, so we have time for 2 questions.
Yeah, with respect to the star clustering bound in the black holes, you always expect the orbital velocity of the stars with respect to the black hole to be much larger than the peak velocity?
Yes, not necessarily much larger, but comparable or larger. And the reason for that is simple. The merger of the 2 black holes occur on a short time scale, shorter than the orbital time of stars far away. Okay? So it's instantaneous. And so imagine a star not moving much during that. So when the black hole gets a kick, suddenly you can go to the rest frame of the black hole, and the star suddenly gets a kick in the opposite direction of equal velocity. Then you can ask if it's still bound to the black hole, and that's just an energy consideration. So you take the initial velocity and the kick velocity, add them vectorially, square that times a half minus gm over r, and you figure out if the star is bound or not. And it really depends on the kick direction and the orbit of the star as to what, and the velocity of the star as to whether it remains bound. But crudely speaking, if the original orbital velocity was above the kick velocity, you would keep the star with the black hole.
Any other questions?
Just
It includes myself. Yeah.
And other such things. I was not offended. One way to potentially avoid possible offenses is maybe to talk about the difference between cosmology and astrophysics.
Mhm.
Those two differences in physics.
The problem with physics is that other than cosmology, the physicists do not have important experiments that reveal new physics anymore. We are doing it with the universe, and that's why cosmology and physics, at least these days, are the same. You know. Maybe if the LHC works better than we expect, it will change. But so far, you know, for the last 20 years, that's what led to the development of string theory, because the experimental aspect of physics was robbed from it. And so cosmology provided a lot of the new insights. We know there is dark matter, dark energy, neutrinos have a mass based on the sun, and things like that. The physicists are lagging behind in terms of laboratory experiments.
Any other questions? If not, let's thank Avi again.